let's take a look of page 6, talking about how do we detect ionizing radiation, that means alpha, beta, gamma, and then some basic way to express in terms of equation, how to write them out. So try to read the textbook for these 4 pages, pause the video and get back to us. Okay, so the answer for detecting ionizing radiation, there are actually 2 kinds of method, CMPS method. The first one is by something called cloud chamber. The second device that you may find out is using the GM counter, which is the previous video I showed you. I talk about the guy in the video using the GM counter, the one with the sound, that one. Okay, we call Geiger-Müller counter because it's invented by these 2 scientists apparently. For the cloud chamber, I will want to show you a video. I'll put the link in the description, and basically they are using alcohol, dry ice, and of course a radioactive source. So this is a radioactive source. It's very tiny, you can see, because apparently for a too large amount, you need to have a license in foreign country as well. For Hong Kong, I think no matter how small you're holding, you should it will still require school to obtain a license. So that's why we don't have it. And anyway, the most important thing is you can see here, this is the trace you can see from different sources. So I think here it includes alpha, which is a very short one, and the beta, which is a very long one, and gamma probably is not very visible. Okay, so I will encourage you to go through this video. They got a very good explanation as well for how cloud chamber will work, and yeah, it will be useful for you. I'll put the link in the description. Here's a paragraph to know about a few keywords that you may use. It's just a language thing. For a radioactive isotope which is unstable, like hydrogen 234 I mentioned, they will become more stable after the decay, and before you decay, the nucleus is called parent nucleus. Again, it's just a name, and it will become 2 things. One is called the daughter nucleus and the decayed product. Okay, don't ask me why it is daughter nucleus but not son nucleus. I don't know why, sorry, I really don't know why, but then that's the name that people define. So daughter nucleus and decay product. So you may write down if you really want to, parents become daughter and decayed product. Okay, these 3 things in general. Here we got some examples from textbook. You may already see some example, and here is some more for you to practice. So again, if you haven't done that, please make sure you try it first, or you can look at my example here. So for maybe I'll try this one and this one for you so that you can practice if you haven't done it. So as we all know, here, I mean, this is like the question. I already know that, let's say, assuming we already know is alpha. So alpha is 4,2. If you remember what we said about this is the mass number, and this is the proton number. In fact, even if you don't know about these 2, the meaning of these 2, you can still work it out. It's very easy. It's something that even primary students know how to do. And then what you have to do is just to balance the number at the top row and the bottom row. So in fact, I do not know what it is unless I have a periodic table. So after uranium, you get to another element. Let's just call it X. How about that? I don't know. You may want to find it out. I think it's radon or something. So in physics exam, we do not expect you to know this also. We don't give you periodic table. I know chemistry, they will give you periodic table, but physics we don't, because we don't expect you to find this out. So anyway, in the exam, they will tell you what element it is. So the most important thing that you need to figure out is the number. So here, you got 2, 3, 8, and 4 here. So in order to balance it, you have to make it 2, 3, 4 here. Same here. This is 92, this is 2, so this is 90. And that's all for this question. So you can try the next one if you want. For beta here, as we all know, beta is electron. So for the mass, even though electron has a very, very tiny mass, we just simply treat it as 0. And for the lower number here, as we said, it is to represent proton. In order to get the whole equation balanced, we will put -1. All right, just like the charge number, -1. And then for again another element that it will emit, it will become to as a daughter nucleus. Let's just put it as Y. How about that? I don't know what that is. From K, I think K is calcium, and then here will become 42 still, and then you should have 20 proton here. So that's why it would be something else, not calcium. Sorry, not calcium. I think K is potassium. All right, my chemistry is not really good. Okay, so here is how you could do it. To just, again, it's just simply matching the number. All right, nothing very difficult. If you're okay with that, then I think you can also try to check the answers for this. So this is also 42, and then let's call it Z, and 222 minus 4 is 218, 86 minus 2 is 84. Okay, so this is how you do it. Similarly, for this one, you may have, by the way, you can put the beta if you like. It doesn't really matter which one is which one. For beta, you may put 0, -1, and you just work out, let's call it A, just a random element symbol. And this remains 87, and this become 38. Okay, so this is, again, very simple work to do. Just balance them. For gamma, it will be a bit different from apparently beta and alpha, because gamma, what it's made of is simply a beam of energy, or you call it photon. So the mass number is 0, photon number is 0, or charge is 0. So let's say we have something called B, element B, and the number is X and Y, doesn't matter what that is. And then what you have by emitting gamma afterwards is still the same number of mass and also proton. Okay, so one thing that you may want to notice is that for some textbook, they may actually put down a star next to it to show that this is at a higher energy state. Alright, or something called excited state. They are excited, so they will emit energy. And afterwards that they will become you know, the normal state or the low energy state. One thing that my students usually ask me when they study this is for beta decay. Alright, I'm not sure if you have the same question. It would be nice if you have the same question. That how come in these, for example, in this reaction, you have the electron, and here if you compare this to this, you seem to have one more proton. So isn't this not appropriate if you think about that? Because you got something extra, and you doesn't seem to have anything lost if you look at all these things. So see if you can maybe pause the video, think about why, and then I will answer you in a second. Okay, so the answer is that the source or the origin of this electron and proton is actually from the neutron from the potassium. So what happened is one of the neutron, you can imagine it kind of break down, decay into two things. One is the electron, which give out as beta particle, and the other one remain as proton, because apparently electron plus proton, it will be neutral. So that's why you have one proton extra here. In fact, if you look at the whole number, 42 minus 20 giving you 12, this is a number of neutron, while previously you have 13 neutrons. So you actually have one neutron less in that case, and that's because, again, that neutron undertake this process. Okay, so this is how beta decay happen. Very interesting. To end this part of video, try to do page 7, this past paper question. Pause the video now and get back to us when you finish. Okay, so here's the answer. For part A, it's very simple. They tell you, as I promised to you, they tell you the elements. So it's RA and RN afterwards. So RA and RN. And so what you have to do is simply by comparing the number. So it was 226 and 88. Just make sure you don't copy it wrong. Emitting alpha, so 42. So just calculate what is remained. So 222 and 86. Okay, so that's all you have to do. One thing be careful is for the symbol between this, it must be arrow. Okay, if you write equal, it is wrong, because equal means it's more like mathematics. You can go backward in that case. So in this reaction is irreversible, so you only go in from left to the right. Part B is something to do with how the penetrating effect or power of different sources. Here will be alpha. So it said there's an experiment done and there's some Kant ray. Imagine the detector is like the GM tube that we talk about, and you can see that the further apart it is, of course the Kant rate is much less. One special thing you may observe is that starting from here, then the Kant rate drop extremely a lot basically, and then for whatever left here is more or less constant. Okay, so that is the observation you should be able to see from the data table here. So part A asking you what causes the Kant rate 9 cm from the source. So that means like all these Kant rate here basically, and that is something to do with the background. Okay, background radiation. Okay, in fact, in your life, anywhere, even nowadays, or I mean right now, when you are sitting in front of the computer, you are receiving background radiation, because from outer space, there are some radiation coming to you, which is usually gamma ray. And if you live in a more rather new building, the rock which built your building would also emit radiation. So that is actually a bad thing if you move to a new house. Number 2 is ask you about what's the Kant rate. Estimate the Kant rate that is due to the source at distance of 2 cm. So as you know, that's roughly around 20 of them is from the background. So at 2 cm, what you have to do is just to remove 20. So 542. I will write down the unit as well. Kant per minute. Okay. And that's it. For number 3, suggest a value for maximum distance that alpha can travel, and apparently it's between 5 and 6. So you may take the average of 5.5 cm. In fact, as I remember the marking scheme, if you write 5 or 6 or between them, it will be accepted. Okay, so but if you can't, if you like write 7, then it's not acceptable. Between 5 and 6 is fine. Number 4, justify your answer. You can simply say after 5 cm, the Kant rate drop drastically. And that is because all the air, because air in itself, it could be like a layer. All this alpha has been ionizing the air in this 5 cm, so you can't ionizing further, and that's why from the data itself, we just have to explain that from the data itself, that is the maximum distance.